In this video, we will discuss about fluorescence, phosphorescence, and delayed fluorescence, and some of its application in the bio-related field. So, first of all, we need to understand uh, in molecules what absorb the fluorescence. It is the chromophore. Chromophores are the one that generally absorb the fluorescence or emit the fluorescence. That generally emit the fluorescence, and they are in molecules are the frequent aromatic rings. Aromatic rings are the one that absorb fluorescence, emit fluorescence or absorb light. So let us first understand some basics with the help of Jablonski diagram. This is the ground state, this is the high energy excited state, and this one is the low energy or singlet state. So what happens in the fluorescence? This one is the example of fluorescence. In fluorescence, when the light absorbs the photon, it will reach to the high energy excited state. After that, it loses some of its energy and come to the low energy or singlet state, and after that it goes down to the ground state. In this process, it will emit a light. It will emit a light at a wavelength that is higher than the wavelength of excitation. Because this is known as excitation steps, and this is known as emission step. Excitation, emission. And for excitation, it requires larger energy because it moves from ground state to more high energy, and for emission, it moves from lower energy compared to the excited state into the ground state. And we know from this formula that E is equal to Sc upon lambda. E is inversely proportional to lambda. Lambda is nothing but a wavelength. So when the energy is high, excitations occurs at a lower wavelength, and when the energy is low, the emission occurs at a higher wavelength. So the emission usually occurs every time occurs at a higher wavelength because of this loss. This is known as fluorescence, and this example is of the phosphorescence. What is phosphorescence? In phosphorescence, the excitation occurs in the similar way. However, the energy is lost, and the photon reach to the forbidden state for the triplet state instead of stabilizing at singlet state, it stabilizes at triplet state. After that, the emission occurs. So in this case, emission occurs at for the higher wavelength compared to the fluorescence. This is known as phosphorescence. What is the spelling? This is phosphorescence. Here, the emission wavelength is even higher than the phosphorescence, even higher than the fluorescence, and this kind of process is called intersystem crossing. Intersystem crossing. And this example is of a delayed fluorescence. What happens is that the excitation occurs in the same way, and it will goes to the stabilize at the triplet state, as in the case of phosphorescence. However, instead of directly going to the emission, it again goes to the singlet state, and then goes down to the ground state. So in this case, the time required for a photon to move from higher energy excited state to the ground state is higher than compared to the fluorescence, and the emission is similar to the fluorescence. So this process is called a delayed fluorescence. And so now from this we have understand that there is always a difference between excitation and emission wavelength because of the loss of energy, and this loss of energy could be due to vibrational loss or thermal loss or any other losses. So now now we will understand some of the terms. What is Stokes shift? Stokes shift is nothing but whenever a molecule, this is fluorescence intensity, this is fluorescence intensity versus wavelength. So far we have understand that when a molecule is excited at a particular wavelength, however it is emitted at a different wavelength because of the loss of energy. So this is usually called excitation curve, and this is emission curve. Now so far we understand why the excitation curve occurs at a higher wavelength and emission curve occurs at a lower wavelength. So excitation curves at a lower wavelength and emission curves at a higher wavelength. So now it is corrected because the energy required for excitation is higher compared to the energy that is emitted during emission. This is known as Stokes shift. And another concept that we need to understand is that saturation. When the saturation occurs, because when the rate of excitation is greater than time required by a molecule to remain at excited state. Excited state. So what happens in this case is that the molecules, the rate at which molecules is excited is continuously is higher than the time required by molecules to remain in excited state. Because of this, the with time the higher energy excited state will become crowded by the molecules, and the ground state will become empty because the time required by molecules to move down to the ground state is lower than the rate of excitation. So when this situation occurs, then we call it as a saturation state. At this stage, we do not get a further increase in the signal of the fluorescence, and our samples get saturated by excitation. Another concept is known as quenching. Quenching is this is key. Okay, quenching. The quenching is usually occurs when the molecules move to the ground state without a fluorescence emission. That is, they usually used intersystem crossing pathway that we have seen in the phosphorescence. So in this, molecules moves to ground state without fluorescence without fluorescence. That is, they use intersystem crossing pathway. Intersystem crossing. That is usually occurs in phosphorescence. Another, one of the most important term in the biology is the photobleaching. Photobleaching is usually occurs when there is irreversible destruction of the chromophores. That is the main component in a molecule that emit fluorescence or absorb light. So this is because of irreversible destruction of chromophores. This is usually occurs due to some molecules, due to exposure of molecules to the light, to the exposure of molecules to the light for an extended amount of time. In this case, the chromophores get lost. The chromophores get irreversible destructed, and the signal will get reduced gradually due to extended exposure of light, and that signal will not be revived, because the main component in the molecules that is responsible for the signal, that is chromophores, are destructed, are now damaged irreversibly because of extended exposure of light. This is usually this problem is usually occurs in the fluorescence, fluorescence microscope. Usually occurs in the fluorescence microscope because of continuous exposure of light. And however, the flow cytometers does not have much problem in the of photobleaching, because their exposure of light to the molecules is very small, or very exposure of light to a molecule, exposure of light is just like a fraction of second to a molecules, whereas in this it can even extends from minutes to hours in case of fluorescence microscope. So whenever we use fluorescence microscope, we need to be take care whether our molecules has photobleaching effect or not, or is susceptible to photobleaching effect or not. So that's all for some background information about fluorescence and how it is related to the biology. Thank you.